start Module 5, Advanced Data Structure. Before this point, we focus on the basics of algorithms. This module, we want to talk about another very important aspect in algorithm design. So that is the data structure. Yeah. So in the first part, we look at a heap sort. Because for this special sorting algorithm, we rely on some special data structure heap. Yeah. So we will use two parts to complete this heap sort. Part A, so that's our heap sort part 1. Yeah. 8.1, Introduction to Heap Sort. All right. So still, the same question we want to ask, why we need to learn another new sorting algorithm. So right now we have learned several sorting algorithms, right? Selection sort, bubble sort, insertion sort, merge sort, quick sort. Now number 6, heap sort. Why we need to add a new sorting algorithm, right? Yeah. So here, because we have some special requirements here. Yeah. Think about in real world situations, sometimes when you determine which sorting algorithm you should use, and you need to make your decision based on your business requirements. Yeah. So here, let's look at some special business requirements, in our decision making for a special sorting algorithm. Yeah. First, we want some sorting algorithm with worst case efficiency, big theta of n log n. Yeah. So that means we don't want the worst case too bad, too slow. Yeah. So we want to control our worst case, not very slow. Yeah. Sometimes we may need. So we want to, avoid that bad bottleneck. Yeah. For this requirement, we know the merge sort can avoid that. The merge sort, its worst case efficiency is this one. Yeah. Other than the merge sort, the other 4 sorting algorithm, they cannot satisfy this condition. Yeah. But we need some more special requirements. Number 2, in place. So we want our sorting algorithm in place. That means the extra storage space used is big theta of 1. That requirement. The merge sort does not satisfy this one. So the merge sort, it is not in place for the merge sort. We need to use the extra storage space, the same amount of space as the original array. If you recall the merge procedure, so you can see that easily. Okay, so it does not satisfy this requirement number 2. Yeah. All right, the third requirement, also another very special requirement. Yeah. We haven't thought about this before. This is a new one. Yeah. So what's that? Maintain dynamic data efficiently. Very special. Dynamic data efficiently. So what is the dynamic data? Yeah. In some real world situation, this special case happens frequently. Dynamic data. Now what's that? So the data, the array to be sorted, does not come in at the same time. It's not the situation is you're not given all the elements at the same time. Okay? You are given the elements one by one during a long period of time. Okay? Yeah. So that's the dynamic data. So when you get several elements of the data, you need to sort it. Okay. A few more elements come in, you need to sort it. For this kind of situation, how to make your sorting algorithm very efficient. So this is a very special requirement. The merge sort, the quick sort, all the sorting algorithm we have learned cannot handle this special requirement well. So that's why we need a completely new sorting algorithm. Yeah. All right. So what do you mean efficiently, right? Yeah, dynamic data. So we know, yeah, we want to handle the dynamic data, but what do you mean efficiently? How fast is acceptable in terms of efficiency, right? Yeah. Let's look at the insertion, because when a new element comes in, you need to insert it into the already sorted array, right? So you basically you do the insertion operation. Yeah. So when you do that, if we record a insertion sort, we have that step, insertion sort. We need big theta of n to do the insertion. Yeah. So that is not very efficient. So we are not satisfied with this efficiency. Too slow, especially when this n is a very large number. It takes a lot of time to get it inserted. It's not efficient. Yeah. So we want better than that. We want significantly better than this one. Yeah. So we want big theta of log n. Take a log on this problem size n. So you will see if we can take the log on it, we improve the efficiency greatly. Okay? Yeah. Huge improvement. Yeah. Okay? Yeah. So that is our goal. Okay? That is our goal for the efficiency insertion of dynamic data efficiency. Okay? Yeah. All right, so an idea. Now we want to solve this problem. So we need to do some analysis to solve this problem. Okay? The idea here, if you do not use a new data structure, it is very hard to solve this problem. Yeah. So far, before this point, when we develop a new sorting algorithm, we always use the array data structure, right? So we do not use any new data structure. But for this one, you have to consider a new data structure. Otherwise, you cannot solve the problem. Okay? Yeah. Here you can see something very general in algorithm design. So that is, sometimes when you need to solve a relatively hard problem. Okay? Yeah. If you only consider the algorithm part, it may not be enough. Yeah. You may also need to consider the data structure part. Yeah. The role of the data structure basically helps you to organize the data in a, in a good way, so it can help you get a solution faster. Yeah. So that's the reason we consider a new data structure. Yeah. Here, we need to see more specifics on this data structure. Okay? So what specific requirement do you need in this data structure? Okay? All right, so look at this function, big theta of log of n. Look at this function. log of n, log base 2, log of n. How do you get log base 2 of n function, right? Yeah. So by the experience we have so far, yeah, because so far we, in our formulas we developed before, many of them contain the log function, right? Many of them contain the log function. Yeah. So think about how do we get that log function? Yeah. Basically, when you get a log base 2 function, basically you have a binary tree structure in your solution. Binary tree. So the log function comes from a binary tree. Okay? Yeah. So from the root going down to the bottom level, yeah. So if your tree is close to the balanced case, then the height of the tree approximately log base 2 of n. So that is the experience we have before. Yeah. So based on that understanding, we should consider a binary tree structure when we design this new data structure. Binary tree. Yeah. We hope we build a binary tree in some way. Okay? So if we can do that, then when you insert a new dynamic data item, you can get big theta of log n efficiency. Yeah. So based on this understanding, yeah, now let's work on the design of the data structure. Yeah. So when we design a data structure, usually people want to make it as simple as possible. Yeah. Most people, they don't like to use a very complicated data structure. Okay? Yeah. No. Yeah, but sometimes probably if you do not use a very complicated data structure, you may not be able to solve the problem. Yeah, that's true. Okay? But in general, we want to use a data structure as simple as possible, and it is also good enough to solve the problem. Yeah. So that's usually, the common way that people use. Yeah. Here, so let's look at the candidates. What are the candidates we can consider to choose this data structure at this point? Yeah. Here I want to compare two candidates. Yeah. The first one, array, because we are very familiar with the array. Okay. Yeah. So most of the time we use array to store our data. Yeah. All right, so that's the first option. The second option, linked list. Linked list. Much more complicated than the array, but it has its own special properties. Yeah. So I hope you know this linked list data structure. Yeah. Yeah. So recall in your CS 2250, this class, C++ and data structure. Yeah. Linked list is covered. Yeah. So I taught this before. So I remember I taught linked list there. Yeah. So think about when you use linked list, how do you implement it? You use special class, yeah. Special methods, yeah. And especially you use pointers, right? You use pointer variables. Yeah. How do you implement link? Right? Link is you use the pointer to implement that link, right? So comparing with array, it is much more complicated. Okay, yeah. But when we use the linked list, we can implement a binary tree. We can implement a binary search tree. Yeah. So if you can remember part of the content in 2250. Yeah. So we can use a linked list to implement binary search tree structure. Okay. So that's the reason we put here as an option here. Okay. All right. Yeah. But here, comparing with array, it is too complicated. The pointers, we want to avoid pointers. Yeah. So most people don't like pointers. Yeah. So we want to avoid it. Yeah. So for that reason, you can see array is much simpler. So we prefer using array here. Yeah. The question is, does it work? Can you use array to implement a binary tree without using pointers? Yeah. So that is the most obvious technical problem we need to solve. Yeah. Otherwise, we cannot use array. Yeah. All right. So we look at the next question. Yeah. Can we use an array directly? Yeah. So now we try array first. Can we use array directly? Yeah, right? Yeah. So what do you mean directly? So we want to maintain dynamic data in an array without doing anything special. Yeah. Directly here, it means without doing anything special. Because we do not know what special thing we should do at this point. Yeah. So that's why we may not be able to do anything special here. Yeah. So if you just grab array and use it directly to manipulate dynamic data, yeah, and you want to make it efficient, we mean this big theta of log m. That means efficient. Big theta of m, it's not efficient. Yeah. The answer is no. If you do not do anything special, you cannot get that. You cannot get that directly. Yeah. All right. So next, should we discard it? Yeah. We don't know how to use it efficiently. Yeah. Do not make that decision so fast. Yeah. Because we need to find a solution. We need to try to find a solution. Yeah. Yeah. If we can, then we can avoid linked list. Otherwise, you have to go to the linked list. So then, most people don't like to use linked list. Yeah. So that's why before we have to switch to the linked list, so we have to try another time on the array. Yeah. All right, so let's try it. Can we modify to make it work? Yeah. So we want to modify it. We can add some special structure in an array to make it work efficiently. Yeah. So let's try it. Okay. So next, yeah. So we want to do this. Build the binary tree structure in an array. Yeah, we want to try this. Yeah. If we can do that, then we can avoid linked list. Yeah. So let's try how to modify the array. Yeah. All right, so let me use a diagram, simple diagram to try to examine the idea for this goal. Okay, yeah. All right, so when we start, so we consider data sorted in array. Yeah. Because If the data is not sorted, we need to sort it. Yeah, we need to make it sorted. Okay. So then when new data comes in, yeah, we need to fix the order. Yeah. So keep fixing it. Yeah. Maintain the ordered data all the time. Yeah. So that's what we need to do. So data sorted in an array. Yeah. And we can assume our current array is sorted. Okay? Yeah. At the beginning, we may need to apply some sorting algorithm to make it sorted. So that's the initial sorting. Initially, the data size may not be very large. Yeah. So we just get it sorted. Yeah. So that's our initial sorting. Yeah. But we do complete sorting only once. After that, then we need to use the insertion way to fix the order. Yeah. So it's not a complete sorting. Yeah. It's just an insertion step to fix the order information. Yeah. All right. So based on that, when new data comes in, yeah, we know the data is not in order automatically. Yeah. But we should not do a complete sorting. Yeah. Too expensive. Okay, too expensive. We don't want to do that. Yeah. So we only want to find the right location for that new element and fix it. Yeah. Okay. Yeah. Now look at how to make it in order. Yeah. And especially we want to do it efficiently. Yeah. So here, based on our background comes from insertion. Insertion step in the insertion sort. Yeah. But if we use the straightforward insertion step as in the insertion sort, we get big theta of n. And we're not satisfied with this efficiency. So we want to drop it. Okay? Yeah. The target, our efficiency target is big theta of log of n. Okay, yeah. So we should use a different way to do the insertion. Yeah. All right, so now let's take a look at the insertion step. Yeah. Still based on our experience. Yeah. So at this point, we have solved many related questions. So we should have some experience we can use for this special situation. Yeah. Yeah. Here, let's look how do we do the insertion. Basically, we can use two different ways to do the insertion. Yeah. So the first way, linear search way, right? So the linear search way, so that's the one corresponds to the big theta of n. Yeah. And this, we don't like that, linear search. But we have another way to do the insertion based on the binary search. So remember, so we use this way many times, right? So when we have a sorted element, 3 ordered element, when we need to insert the 4th element, we compare with the one in the middle. That's the binary search way. Okay? Binary search way we can do better than the linear search way. Yeah. So for that experience we should use the binary search based insertion here. Okay? Yeah. So you can see our old experience is important. Yeah. So in this simple example, we need that. Okay? All right, so the next question. So now we have some more idea. Yeah. The next question is how to get it, how to make that happen, how to make our data structure support binary search insertion. That's the question. How to make our database, how to make our data structure support binary search type insertion. Okay, yeah. Yeah, but here we complete our first introduction video. So we will answer this question in the following videos. All right, so we stop here. Yeah.